Okay, today we're going to cover the routing algorithms and some specific routing protocols that we use in the internet. So which are RIP, OSPF, BGP. But before that, we're going to learn the main principles of the routing algorithms, including three approaches. The first one is the link state. The second one is the distance vector. And the third one is the more practical one, is the hierarchical routing. And then finally, we will gonna complete this chapter by broadcast and multicast routing. How do we broadcast and multicast? Recall that we are covering so far the case of the unicast, but in the last section we're going to cover the broadcast as well as the multicast routing method. So remember that we have routing and we have forwarding. So the routing algorithm was responsible for the end-to-end path through the network. On the other hand, the forwarding was responsible for determining the local forwarding at this router. So if your router receive a packet, and in the packet header we have the IP destination address, and if the IP destination address falls within one of these range in the forwarding table, then we forward that output to we forward that packet to the respective output in the table. For instance, if your IP destination falls within the address range 1, then we need to move this packet to the output of 3. If it falls within the range of address range 2, then we move this packet to the output of number 2, and then address range and so on. So in summary, routing is responsible for end-to-end path determination, whereas forwarding table is responsible for the local forwarding. So where to forward the incoming packet to the output link. Okay, so routing is I think is the most critical part of the network. So how to carry the packet from one point to another point. So we need to model this routing. So we use the graph theory in order to explain this routing algorithm. So let's start with the graph theory. Graph was consist of two parts. Let's say our graph is G is equal to N and E. N was, remember, it was a node, and E was edge. So in our case, N node is the set of routers. In this example is a U, V, X, W, Y, Z. E stands for set of links. In our case, is the links in our case that connect two routers. So for instance, the UV link, UX link, VX link, VW, WY, XW, and so on. So in this graph abstraction, the N is the node, E is for the links that connect the routers. So one of the main terminology that we're going to use is the call cost, the cost of the link. For instance, CX X prime means the cost of links between X and X prime node. If you want to give an example, cost of WZ, you know, what's the link cost link of what is the cost of the link between W and Z routers? As you see in the graph, this link has a cost of 5. This link has a cost of 2, for instance. The link between U and X has a cost of 1. The link between U and V has a cost of 2. So cost could always be 1 or inversely related to the bandwidth or inversely related to the congestion, network traffic. But if we have we can have a equation or representation like this: cost of path from x1, x2, x3, xp. So that means the total cost is gonna be the sum of all these path cost link. So which means the cost between x1, x2 plus the cost of the link between x2 and x3 and so on. So the question is here, what we are trying to find is what is the least cost path between U and Z. In our case, U is the source and Z is the destination. So what is the least cost, minimum cost path between U and Z? As you can see, there are many possible ways to reach from U to Z, but among these potential paths, which one is the least cost path? So that's our question that we are trying to answer. And who is going to answer this question? Routing algorithm. That's what routing algorithm do job. So what's the job of the routing algorithm? Is trying to find this least cost path between source and destination. In our case, let's say U and Z nodes. Okay, so we defined the main task of the routing algorithm, and now what are the solutions? So there are different approaches to solve this problem. So that's why we classify the routing algorithm as follows. The first classification is based on the information about the node, whether it's global or is decentralized. In global routing algorithm, all the routers in the network have a complete topology and the link cost information. So this approach is used by link state algorithms. All the routers in the network have the same and the complete topology as well as the information about all the links in the all the link cost in the network. But in the decentralized approach, we say no. Each of the router doesn't have to know the link cost of all the link cost in the network. If he or she knows only the link cost of its neighbor, that is sufficient. So therefore, in this second approach, which is the decentralized, routers knows physically connected neighbors and link costs to the neighbors. So it knows two information. The first one is it knows the link cost of the physically connected neighbors and the neighbors to the other nodes link cost information. Iterative process of computation. So by iterative process of computation and exchange of information with neighbors, it can have it can set up a end-to-end path. So this approach is used by distance vector algorithms. We can classify these routing algorithm in terms of static or dynamic, to be dynamic or static. In static case, routes change slowly over time. In the dynamic case, as the name implies, routes change more quickly with a periodic update or in response to the link cost change. If any link cost value is changed, then the routes change more quickly in case of dynamic routing algorithms. Okay, so after this classification, let's start with the first one, which was the global approach, that all the routers have the complete network topology as well as the link cost of all the links. So the first one, we said that is a link state algorithms, and the most popular algorithm in this case is Dijkstra algorithms. So let's look at the Dijkstra algorithms. In this algorithm, network topology, the link cost known to all the nodes in the network. So all the nodes, all the routers in the network, they have the same information, which is the complete network topology and the cost of all the links in the network. And how do we obtain achieve this, is through the link state broadcast. So with this link state broadcast, every nodes get these two pieces of information, which is the complete network topology and the link costs. That means all the nodes receive the same information. So all the nodes have the same information. And then the Dijkstra algorithm, after obtaining this information, it computes the least cost paths from one node, which we call source, to all the other nodes. And then it establishes, it forms the forwarding table for that node. And we have, this is an iterative algorithm. After k iterations, it knows the least cost path to the k destinations. So the main idea here is trying to find the least cost path to k destinations. So in order to explain these Dijkstra algorithms, we're gonna give you some notation that we use. So the C of x and y is a link cost from the node x to y. And if not direct neighbors, then we put this as an infinity. So if two nodes are neighbor, we put a value. If that node is a not direct neighbors, then we put the value of infinity. D of V is the current value of cost of path from source to destination V, and P of V is the predecessor node along path from source to V, and M prime is a set of nodes whose least cost path definitely known. Okay, let's look at the Dijkstra algorithms in details. So we have the first step is the initialization step, where the n prime, remember, it was the set of nodes whose least cost path definitely known. So we start with the u, and for all nodes v, if that node v is adjacent to this u, which is the starting point, in our case the source, then the d of v, what was the d of v, is the current value of cost of path from source to destination v. We're going to assign the link cost between u and v to the d of v. If it's not a direct neighbors, then we assign infinite value to that d of v. And then we're gonna put this in the loop. We're gonna find the w that not in n prime such that d of v is a minimum. And we add this w, the new node, to the n prime set. And then we update d of v for all the v that is adjacent to the w and not in n prime. So we use this distance vector, which is minimum of d of v, or the dw plus the new nodes plus the cost of the this new link. And then we iterate this until we complete all the nodes in the networks. For, the number of loops is equal to the number of nodes in the network. Okay, in order to understand in details, let's have an example together. An example for Dijkstra algorithm. And this is our sample network, which consists of U, X, W, V, Y, Z. So we have 6 routers in this case. And the link cost is shown on the network figure as you see. For instance, the link cost between U and X is 5, U and W is 3, and U and V is 7. So in initial case, we start with the source, which is the starting point. So the end prime, it was empty set. Now the first node that we're going to add is U, the first node. And let's calculate the D of V. D of V is the current value of the cost link. As you see, between U and V, the link cost is 7. So we put the 7, comma, P of V was the predecessor node. So what's the predecessor node? Is the node that before this node. So the originating node. And then DW is the current value of the link between U and W. As you see, the link cost between U and W is 3. And where these links originate, the predecessor node is again U. And then we have D of X for the X routers. And the current value for that link is 5. The link cost between U and X is 5, comma, what's the P of X? In this case, the predecessor node is again U. These are the direct nodes to the node U, as you see. We have 3 direct nodes. That's why we have this predecessor node to be U. But for the Y and Z, since we don't have direct connection, they are not directly neighbor. So that's why we assign infinity to Y and infinity to Z, because the link cost, if it's not that direct neighbors, we assign value of infinity. That was the initial step. And then according to algorithm, we're gonna choose the minimum, the least cost path. So what is the least cost path in this case? This one has a cost of 7, this is 3, this is 5. Which one is the minimum? Of course, the 3 one, the W node. That's why we add this W to the n prime set. And then we recalculate the current value because the W is now has a link to the U. So the new current value of cost between U and V, initially it was 7, but now we have the lesser cost. So we can reach to the V over the W now because we add the W to the network. So is 3 plus 3 is now 6, which is less than 7. So that's why the new value for D of V is 6. In this path, what's the predecessor node? Just the node before the V is W, of course. And then we are done with the DW, that's why we are skipping. Now let's look at the D of X. D of X is still, this is 5, and we have an alternative path over W, but the cost is 3 plus 4 equal to 7. So because of this is minimum 1 is less than 7, we keep this value. So now we can reach to the Y through the W, as you see. the value for d of y is equal to 3 plus 8 is 11. And what's the p of y? Means the predecessor node, the node just before the y is w. That's why the value for this case is 11 comma w. Still, we don't have a direct access to the z or through the w. That's why we keep this infinity. So in this step, what is the minimum coast path? In this case, we have 6, 5, 11. Of course, is the 5. That's why we add this node x to the n prime set. Okay, we recalculate that d of v is still the minimum path to the v is 3 plus 3 is 6, and the p of v is w. Now we are skipping wx. We are done with these two nodes. Let's look at the d of y. Still, we keep the cost of 11, comma w. Now, because we are done with the x, we add this x. We can reach to the z through the x. So let's calculate the d of z. In this case is 5 plus 9. So the end-to-end cost is 14, comma, the p of z is equal to x, the predecessor node. The node just before z is the x. Okay, we reach to the z through the x. So now we apply that criteria again. What's the minimum cost path in this case? Least cost path. We have 6, we have 11, we have 14. Of course, is 6. So that's why we add the node of v to the n prime set. And then now we are going to calculate the new cost for the y. Looks like we have the less cost path. So initial was 3 plus 8 was 11, but now we can reach to y through the v, right? And one of them is 7 plus 4 is equal to 11. No, we have another alternative. Is 3 plus 3 plus 4, which is equal to 10. So the new value for d of y is this path, and it has a total cost of 10. And what's the predecessor node, which means p of y is v. So we reach to the y, and just before that the node is v. So that's why the p of v is equal to v. And the d of z and p of z is still 14 comma x. So we keep that values. Now among these two, which one is the minimum? Of course, this 10 one, right? 10 is less than 14. And then we add the node of y to the n prime set. So, and then what we left is we come up with a new path, which is from through the y, right? How can we do that? Is 3 plus 3 plus 4, and then plus 2 is equal to 12. We have the last cost path compared to the previous one to reach to the z, and then the new value for d of z is 12, and the p of z is equal to y. And that was the last one, and we add the node z to the n prime set, and we are done with the algorithm. So how we're gonna put this into the shortest path tree? We're gonna just follow the predecessor node, okay? Is from z to the last one was z, of course, y, v, as you can see, right? W and u. And in order to reach the X, we have the U, direct path. So, as you see, we construct the shortest path tree by tracing the predecessor nodes. We have the Y, we have the V, then we have the W, and then we have the U. Between U and X, we have this link. So this is the shortest path tree that we constructed by using the Dijkstra algorithm. In some case, the ties can exist. If the ties, what's the ties? If the costs are equal to each other, for instance, in case of number 3 step 3, if this two has a 10, then we just select one of them arbitrarily to break the tie, okay? Another example, second example for the Dijkstra algorithm. So now we have this network topology, which consists of 1, 2, 3, 4, 5, 6 nodes. In other words, routers. And these are the links that is written on the figure. So our source is U again, destination is Z. What we are trying to do is trying to find the least cost path, right? Shortest path. So let's start again with the U. Now the D of V has a value of 2. The link cost between U and V is 2. And the predecessor node is U because it's a direct neighbor. For the W, we have a direct neighbor. The D of W is 5, and P of W is U. For the X node, the D of X is 1, the link cost is 1, and the P of X is U because it is a direct neighbor. And for the D of Y, it's not directly connected, it's not a direct neighbors, so that's why I put infinity. And for the Z is again infinity because it's not directly connected to the source. So among this one, what's the minimum cost path is this, right? 1. So that's why we put the X node to the n prime set. Now we recalculate D of V. D of V is still 2, and P of V is U. And then DW, D of W, now it's what? It's 4 because we have a alternative path. So that was the initial path. 2 plus 3, no, because we have the X 1 plus 3. We have our alternative route now is 1 plus 3, which is 4 through the X. We can reach to the W through the X. The value of the DW is going to be 4. P of W is going to be X. And then for the Y, now we can reach to the Y through the X. And the D of Y is 2 because 1 plus 1 is 2. And the P of W is X in this case. And Z still is not reachable because it's not a direct connected, so we keep it infinity. Now we have link cost of 2, 4, 2. As you see, we have a tie here. So both V and Y has a value of 2. Which one we're going to select? Arbitrarily, we're going to select one of them. So let's select the node Y. So that's why I put the Y to here. So in the step 2, we have the value of, again, D of V is still 2 comma U. Now the W has a new value because we add this node Y, and the new cost is 1 plus 1 plus 1 plus is 3, which is less than the previous one. So that's why we update the value of DW. And the PW is going to be Y because it's reachable through the just the node before the W is Y. Now through the Y we can reach to the Z. We can calculate the D of Z is 1 plus 1 plus 2. 2 plus 2 is 4. So that's why we have 4Y. Now we have three values, 2, 3, 4. Which one is the minimum one? Of course, this 2, 1, right? So that's why we add the V to the N prime set. And then what we left with is DW. Still the list one is the 3Y, and the Z is still the list cost is 4Y. So which one is the minimum? Of course, the W node. So that's why we add the W to the N prime set. And what we left only is the node Z, which has 4Y values. And then we add the Z, and then we are done with all the nodes in the network. In order to construct the shortest path, tree. So based on this predecessor node, remember from the previous, by tracing the predecessor nodes, we construct a shortest path tree. So the first one is Z, of course, and then the next one is W, as you see, Y. Okay, it's Y, Y, as you see, the Z is connected to Y, the W is connected to Y, and then, so by tracing the predecessor node, we construct the shortest path tree from U, as you see from here. And from there, also we can construct the forwarding table in U. The destination is V, as you see. And we can reach to a destination with which output with the link of UV. And the destination is X. It can be reachable through the UX link. Y is, if destination is Y, we can reach through the U of X. And W we can reach through the U of X, and Z we can reach through the U of X. So these are the direct link that we can reach to the other nodes. So based on this algorithm, we have two outcomes. The first one is the shortest path tree from U, and we have the forwarding table in U. Okay, so as you see, the Dijkstra algorithm is one of the most popular algorithm in case of link state method. That was the performance. Let's look at some complexity and the issues that we have with this algorithm. So first of all, let's look at the algorithm complexity, computational processing and complexity. Assume that we have n number of nodes, and each iteration, you see for each node we have an iteration. We need to check all the nodes, which was W in our case, that is not in n set, n prime set. So that's why we need n times n plus over 2 comparison, which is O(n) square complex. But people, they come up with kind of lower complex algorithm in order to reduce the complexity of these algorithms. So there are more efficient implementation which is possible with the complexity of O n log n. And one of the problem here is the oscillation. So you can reach to a node from different paths, which may result into the oscillations. Okay, that was about the first approach. What was the first approach? It was global routing approach, where all the nodes in the network has a complete network topology and the cost of all the links. Of course, this is complex, right? But in the second approach, we have a kind of distributed or decentralized, where you only know the network topology and cost of your neighbors only. And if everybody knows that information, right? If each node in the network knows the cost of their neighbors, and if they share with each other, then you can come up with the global coverage, right? So this is the second approach. Let's see how this works. So this approach is used by the distance vector algorithm. Also, it utilized the Bellman-Ford equation. So what we use here is the following matrix that we use. The matrix is called dx of y. What does it mean? Is the cost of least cost path from node x to node y. Then, how do we calculate this? We have the two values. One of them is the cost to the neighbor, as I mentioned. The cost of link cost from x to the neighbor v. But our destination is not v. Our destination is y. So we reach to the y through the neighbor v. So that's why we calculate the first cost, which is the cost from x to v, our neighbor, and from neighbor to destination, which is dv of y, cost from neighbor v to the destination y. When you sum up this, and you come up with a value end-to-end cost, and we take this all over all neighbors v of x. So we calculate this value for all the neighbors, and among these we select the minimum one. So that's how the distance vector algorithm works. Let's look at explain this with an example. So in this case, the previous example, in order to compare, we have this network topology, which consists of 6 routers or nodes, and the link costs are given. You can see clearly the distance, the cost from V to Z, cost from V to Z is what? Is 5, right? And from X to Z is 1 plus 2 is 3, right? From W to Z is equal to 3. In this case, we have two, as you see, we have 3 direct neighbors. So our source is U. In this case, we have 3 direct neighbors, right? The first neighbor is V, second is X, and third one is W. So we are going to calculate first the cost of the link cost between U and its neighbor. So the first one is the cost between U to V plus from V to Z, which is the destination. And the second one is the cost of U to the X, because the second direct neighbor is X. Sorry. And plus from X to destination, which is X to Z. We in our case is dx of Z. And then the third neighbor is the cost from U to the W is this plus the cost from W to Z. So let's calculate together. And we're going to calculate three values. And after calculating these three values, then we're going to select the minimum values, which is going to give us the shortest path, okay? So the CU of V, the cost between U and V is what? 2. Let's put 2 here. Plus, what's the dV of Z? The cost from V to Z. We said is 2, 1 plus 2, 1 over X over Y over Z, right? 2, 1 plus 2 plus 1 plus 2, which is equal to 5. 2 plus 5, which is equal to 7. Let's calculate the second potential path over the neighbor of X. The cost from U to the X is 1 plus the cost from X to Z is 1 plus 2 is 3, right? 1 plus 3 is equal to 4. And the last neighbor is W. The cost from U to W is 5 plus from W to Z is 3, as you see here, through here, W, Y, and Z. 1 plus 2 is equal to 3. So the first, the cost for the over the first neighbor is 7, second neighbor is 4, and third neighbor is 8. Which one is the minimum? The X one is the minimum. So then we select this path. So let's go over the algorithm again. What we are trying to is trying to estimate the least cost from node X to node Y. In other words, from node X is a source, node Y is the destination. So the node X, which is the source in our case, maintains the distance vector d of X, which is equal to dx of Y, and we calculate this for all the Y that is element of n set. So the node X, in our case, is U, knows the cost to each neighbor, V. So, and we notate this with the C X of V, and then maintains its neighbor distance vectors. For each neighbor, we gonna calculate or maintain this value from V to Y. So in summary, we need two information in order to calculate dx of Y is equal to CXV plus dV. So therefore, any node in this algorithm, in our case is the X, need to know and maintain two values, cost to the neighbor and from each neighbor to the destination cost. So we need to know these two information and keep update this in our table. So how do we update this information? Because it depends on the others. So each node sends in its own distance vector estimate to neighbors. So when the X receives new distance vector estimate from neighbor, and it's gonna update its own dV using the Bellman-Ford equation, using this. So, and this is an iterative also, because each local iteration is caused by if some link can be down or can fail or can change, whatever. So in any case of local link cost change, we're gonna update our table and the dv update message from neighbor. And whenever a link cost change, so we get this information from the neighbor. So in distributed approach, each node notifies neighbors only when its distance vector changes. So the neighbors then notify their neighbors if necessary, okay? So in summary, we're going to wait for the change in the local link cost or message from neighbor. So as a node X, I'm going to wait for the change in the local link cost or a message from neighbor, and then recompute my DV estimate. And if any DV to any if DV to any destination has changed, I'm gonna also notify this change to my neighbors. As you know, the other neighbors notify me with this change, and if this change is gonna affect me, what does it mean? Affection is if DV to any destination has changed, I'm gonna also notify my neighbors about this change. So let's give an example to understand how this distance vector algorithm works. So very simple network, which consists of three nodes, routers, X, Y, Z, and their link cost is 217, as you see. Now, in initial case, this is the node X table, this node Y table, this node Z table. How do we read this? The line, this is the column. Cost from X to X, of course, is 0. Cost from X to Y, the link cost is 2, as you see. And the cost from X to Z is 7. So in initial case, node X is gonna form its table this way. And the rest is minimum, the infinity, because from Y to X, we don't know. So that's why we assign infinite. Now let's move on to the node Y in the first step. So this is the first step, and this axis is time, as you see. In the first period, everybody is gonna calculate its cost to the neighbors. So the node X table calculation we already mentioned. Now let's move on to the node Y. So the cost from Y to X, from Y to X is 2, right? And the cost from Y to Y is 0, and cost from Y to Z, is 1. And the remaining are infinity in the first initial step. And let's look at the node Z, how it establishes its table in the first initial step. So the cost from Z to X, as you see, is 7. The cost from Z to Y, is 1, and cost from Z to Z is 0. So as you see in the first period, in the first time slot, all the node calculate the cost to its direct neighbors. Now it's time to share this information among the neighbors. So first of all, the node Y is going to share its information is 201 in the second period, and the node Z is going to share its information with the X, which is 710. So based on this information, let's look at calculate this distance DV estimate. What was the DV estimate? Remember, it was the cost to the neighbor and neighbor to the destination. In case of X, dxy, because this column is the cost from X to Y. So let's calculate together, is equal to cost of XY, cost from X to Y, plus cost from Y to Y. And then the next one is cost from X to Z and from Z to Y, because I can reach to the Y in two ways in this network, right? I can have a direct connection, direct link, which is this, and then I can reach to the y through this z, right? That's why it's the cost from x to z and z to y. So let's put the values here. The cost from x to y is 2, and cost from y to y is 0, as you can see from here. 2 plus 0 is equal to 2. And the cost of x to z, cost from x to z, is here. Z to x also, x to z is here. 7, and plus cost from z to y. Z to y is this 1, right? We are utilizing this information. Cost from z to y, y to z. Z to y is 1, and we put this 1 here. Now we have 2, we have 8. So the link cost through this link is 2, through this one is 8. Which one is the minimum? Of course, this one is the minimum. That's why we put 2 here. Now let's calculate the cost from x to z. Initially, it was 7, right, in the first time slot. But now, after I get this DV estimates from my neighbor, I need to update this. And let's look, by updating, we need to calculate this again, which is dx of z. DV estimates from x to z is equal to xy, the cost from x to y, plus the cost from y to z. X to y, y to z. So there are two paths, right? In this case, one is the direct path, x and z. The other one is through the y. So this is the through the y, and this is the direct path, which is the cost of x of z and plus z to z. So let's calculate together. And cost from x to y, is 2. We just calculated. Put it here 2. And from y to z, y to z is 1. So we put it here 1 to here. 2 plus 1 is 3. Now let's look at the cost from x to z, and then z to z, as you see from this table, is equal to 0. X to z is 7, z to z is 0. 7 plus 0, 7. So now we have two values. Through this one is the cost is 3, through this one is the 7. Which one is the minimum? Of course, through the y. So that's why we select this path, which is 3. And then you do all this kind of in the second time slot. We do update the node y table as well as the node z table. Okay. And then in the second time slot, as you see, all have the same information. So it converges. These three nodes, they share this information. And in the third step, as you can see, all the node has the same information, same table. So that was our target, actually, like in the previous case in the link state. In the link state, all the node has the same information, but that information was broadcasted and all the nodes received the same information. But here, you know only the information about your neighbor, and with neighbor, by sharing the information, you reach to the same information as the previous method. So all the nodes in the network ultimately is going to have the same information as you see in the third step. So what we said, the link cost can change, right? And the node it detects this cost change, and it's gonna update routing information and recalculate distance vector. If after this calculation any DV changes, each node is gonna notify neighbors immediately. For instance, so in the previous example, the cost between XZ is 50, and between XY it was initially 4, and this was 1. Assume that the link cost between XY is changed from 4 to 1, right? In this case, the Y detects the link cost change, and it's going to update its distance vectors, and it's going to inform its neighbors. Who are the neighbors? X and Z. Assume that in time slot T1, the Z is going to receive this update from Y, and it's also going to update its table, and it's going to compute new list cost to the X, and sends its neighbors its DV. And in the third time slot, Y is going to receive Z's update, and it's going to update its distance table. As you see, the Y's list costs do not change. So Y doesn't send that message to Z because initially the Z can be reachable through the X can reach to the Z through the Y. The total cost was 4 plus 1, 5. Now it becomes 2 even. So since this 50 is much larger than this 2, so it's not going to affect the Y least cost path. But assume that in the previous example, the link cost between X and Y changed from 4 to 60. Of course, this is going to affect the routing because 60 is greater than 50, right? So the X can now reach to Z through the 50. Initially, it was through the Y. Now it can directly select this path because this has a less cost than the previous one. Anyway, so the node is going to detect this cost change, and then it's going to update its routing accordingly, as we mentioned in the previous slide. Okay, in summary, let's compare these two methods, which was link state and the distance vector algorithms. So in terms of message complexity, the first criteria that we're going to compare is the message complexity. In the link state, we have n number of nodes and e number of links. So the complexity of the message sent is O n times e. And then in the distance vector, we exchange between neighbors only. You can see the difference. So in the first one, we select, we are going to send a message. What's the number of message with the complexity of ONE for all the neighbors and through the links. And in the DV approach, we just exchange message between our neighbors, which is much less than the LS case in practice. Of course, in the DV case, the convergence time varies depending on the number of neighbors that you have. What about speed of convergence? As you see in the previous example, after 3 steps, it converges. All the node has the same table. In case of link state, the complexity of ON square algorithm requires ONE message, and we may have some oscillation problem that I mentioned. And in the DV case, the convergence time varies because of the number of neighbors and so on. And we may have some routing loops and count to infinite problem. In terms of robustness, if you compare these two algorithms, what happens if router malfunction? What happens if, you know, router provides some, you know, error information or wrong information or incorrect link cost, let's call it. In case of link state, the node can advertise incorrect link cost, and each node is going to compute only its own table. Okay, so if I receive an incorrect link cost as a node, I just compute my own table. But this is not the case for the DV. If DV node can advertise incorrect path cost, because neighbor are, I'm gonna, you know, advertise to my neighbor, each node's table used by others. So if I do a error, then this error is gonna propagate through the network. So that's how is the comparison in terms of in case the router malfunction. Okay, so in the routing algorithms, the last topic is the hierarchical routing. So these two methods are, let's say, is kind of course, they are practical, but they are based on some theory. What do we do in practice, in real life? So what we do is actually is a hierarchical routing. When we implement these methods in practice in the internet, for instance, we use some hierarchy. So what is the hierarchical routing? So far, you know, we assume some, you know, idealistic case, but in practice, okay, what are these idealistic case? We assume that all the routers are identical in the network topology or the network example that I gave it to you guys. But in the practice, all the routers are not identical. And network is not flat. So in one, you know, we have different kind of companies and vendors like Cisco, like HP, Aruba, you know, AirTies and so on. So all the routers may not be identical, the algorithm that they use, and so on. And considering the scale, in this example, we just consider 5-6 nodes, but in realistic life, millions of, you know, destination and the routers maybe. So assuming that we have 600 million destination, we cannot store all these destination in the routing tables. And, you know, if you exchange just a piece of information with 600 million, you know, in each time slot, this routing table exchange would, you know, is gonna swamp the links. So that's why we need to come up with a architecture or hierarchy to handle these issues in practice when we implement these our routing algorithms. So what was the internet? Internet was a network of networks. This is my network in Gebze Technical University. That's another company network. So each network admin may want to control routing its own network. Of course, each company, each institution, they want to control their routing in their network. So what is the solution? We aggregate routers into regions, which we call autonomous system, AS. Routers in same AS, routers in the same AS run same routing protocol, which we call intra-AS routing protocols. Routers in different AS can run different intra-AS routing protocol. So this is my AS. Within this, I can, you know, force all the routers to use the same routing algorithm, but I cannot control the other companies' intra-AS routing protocols, so it's up to them. And we have the gateway router at the edge of its own AS, has a link to the router in another AS. So we said we aggregate routers into regions which we call autonomous system, AS. In this example, we have 3 AS, AS1, AS2, AS3. This is a group of routers. Now, the question, of course, this AS, even though I control AS1, the other controls AS2, and the third guy control the AS3, but eventually we need to exchange the data, right? Packets. So that's why we need to come up with a forwarding table. So the question is, who is going to control or update, maintain the forwarding table? The answer is both intra-AS as well as the inter-AS routing algorithm. So inter-AS, what's the inter-AS? Is the routing that manage the routing between two different AS autonomous system. Intra-AS is the routing algorithm that runs within a single AS. So the routing inside the AS and intra-AS, as the name implies, is the routing algorithm that manage the routing between multiple AS. So in summary, as you see from the figure, the forwarding table is going to be configured by both intra-AS as well as intra-AS routing algorithm. Because intra-AS is going to set entries for internal destination, and the intra-AS and the intra-AS sets entries for external destination together. So let's look at the inter-AS task. Assume that router in AS1 router in AS1 receives datagram destined outside of AS1. So router should forward packet to gateway router, but which one? Okay, I receive as an AS1, I receive a datagram, and I need to forward to this another AS. But how? Which gateway router that I should send? In order to achieve this, AS1 must learn which destinations are reachable through AS2 and which one are reachable through AS3, which is my neighbor AS, right? I have two neighbor AS, and I should have the information about them. Those two, AS2 and AS3, are which destination are reachable through this AS2 and AS3. And we are going to propagate this reachability information to all the routers in my routing, which is 1A, 1C, 1D, 1B routers. So I'm going to get this information, and I need to distribute this information among my routers within my AS1, which are 1A, 1B, 1C, and 1D routers. Okay. Let's say, example, we are going to set the forwarding table in router 1D. And as I mentioned, assume that AS1 learns that subnet X reachable via AS3. AS3 gateway 1C. As you can see from this figure, the AS3 is reachable, is connected to my AS1 through the gateway 1C, right? But not via AS2. So the inter-AS protocol propagates reachability information to all internal routers. So this inter-AS protocol is going to distribute this reachability information to all the internal routers. And the router 1D in AS1, as you see, determines from the intra-AS routing information that its interface 1 is on the least cost path to 1C. So the least cost path from to reach to X is through the 1C. And it's going to install forwarding table entry as X1. Now, how we're going to choose among multiple autonomous systems. Now suppose AS1 learns from inter-AS protocol that subnet X is reachable from not only AS3, also from AS2. In the previous case, the subnet X was reachable only through the AS3, right? Now we add another complexity, so this subnet X is reachable through the AS2 as well. So in order to configure the forwarding table, router 1D must determine which gateway it should forward packets in order to reach to destination X. That is also job of inter-AS routing protocol. It's not the intra, it's the job of inter-AS protocol. So which gateway we should the 1D use in order to destin the packets to destination X. So let's summarize. Now assume that AS1 learns from inter-AS protocol that subnet X is reachable from AS3 and from AS2. So in order to configure forwarding table, router 1D is going to determine which gateway, right, it should forward the packets for the destination X. We said that this is the job of inter-AS routing protocol. So in the second step, use the routing information from intra-AS protocol in order to determine the cost of least cost paths to each of the gateways, and choose the gateway that has the smallest least cost, which we call hot potato routing. So there are multiple least cost. We're going to select. There are potential many paths to reach to this subnet X. We're going to select the path that has the least cost, and then determine from the forwarding table that interface 1 that leads to the least cost gateway, and then we're going to enter this X1 in the forwarding table. This is how we update the forwarding table.